Hi and welcome. Let's jump right in. I have a question for you. What do you predict does the future of our data centers look like? Do you think, you know, we will move everything to main memory? Do you think that we will use specific protocols, specific network stacks? Will everything be done with gRPC, with RPC, with like what do you imagine will the future of our infrastructure be like? The paper that I present today is built upon two or let's say three main premises or assumptions actually. So up until now, we could observe that single threads aren't scaling, or vertically we aren't scaling as fast as we initially thought. Moore's law doesn't apply anymore. Alexander, the main author of the paper, mentioned in the future, as request rates go up, we expect to become CPU bottlenecked. And like this is like the main premise: horizontal scaling, distributed systems will be more dominant. That's a trend that we could observe until now. But there are two more interesting trends that we'll look at. One of them is, moving everything to main memory is getting cheaper, a lot cheaper. The entire application's data set will fit into the main memory. And the other assumption is that the TCP/IP stack will be the next bottleneck, and it should, like the FaRM, the papers, the authors suggest RDMA as an alternative. They think that RDMA, which we will get to in a moment, is the future. And that's the future that this paper is preparing us for. So what is this RDMA thing? Sorry. RDMA stands for Remote Direct Memory Access. So it's reliable, it's fast, and it's affordable. Let's drink all the RDMA Kool-Aid, shall we? So it's reliable in the sense that requests are sent through queue pairs, and network failures are immediately visible because your connections get terminated. It's fast because we don't have all the overhead. The network interface cards perform all the requests, so we bypass the kernel. We bypass the remote CPU for our read and write operations, and everything happens in the user level. And we don't have like any of these protocol stack overheads. And recently it's become more affordable. I mean, RDMA is like ancient technology. I mean, it depends on what you see as ancient, but it is pretty old high performance computing technology, and it's recently become like more affordable through Rocky, and the RDMA over Converged Ethernet. And it's just hardware support for RDMA over Ethernet. Previously, you had the InfiniBand InfiniBand cables that weren't affordable, and so it's become more ubiquitous. All you need now are these widely available Ethernet cables and data center bridging extensions that you can find anywhere. So these are like the hardware developments that have made this paper possible in the first place, or even worth considering. Sorry again. So how does RDMA work? So the NICs, as mentioned, perform the RDMA request. We bypass the kernel, we bypass the remote CPU for the read and write operations, and the steps are the following. The server's NIC. So you have here we have machine A and machine B, and machine A wants to read machine B's memory with RDMA. Here we have a message passing example. So the server's NIC registers the memory regions in the NIC's page table, which is just a virtual physical page mapping, and then it sends its capabilities, like machine B sends its capabilities to machine A, and says, here are like my available memory regions. Then machine A says, oh, that's great. Did I get a message? Stay in the call, sorry. Google Meet was playing around. So then machine A says, oh, great. Now I know what memory regions you have, how I can address single blocks of memory with the specific offset. And then it sends the request, and it sends through its NIC. So the CPU sends the request to the NIC. The NIC then accesses the other NIC, and through direct memory access without any CPU interrupts, we read the RDMA and send the response back. And all of this happens, the operation gets executed with DMA and in a cache coherent way. And also keep in mind that in this paper, the hardware, the NICs have very modified. The RDMA has also been modified, and the writes are committed in an increasing address order. Now, how fast is RDMA? Here we have like a benchmark with 20 machines, random reads, and Rocky networks, and as mentioned, the optimized NICs. Like here at the bottom, we have TCP/IP with remote procedure calls. Then we have the same thing, but instead of TCP, we have RDMA, again, remote procedure calls. And then at the top, like this alone was a twofold speed up. And then at the very top, we have the RDMA with the FaRM machine, and then again, we have twice the throughput. Something to mention here is that we don't talk about UDP, and that is because, as it's said in the paper, UDP in these examples is half as fast as TCP, which I didn't quite get, since the new HTTP, like quick HTTP is built upon UDP. So that's something that I didn't quite get. I'll have to dig deeper into it, but what the authors meant by why they're not considering UDP. And also the other thing to mention is that local memory still wins, like spatial locality, locality-aware optimizations. Either way, local memory is always still 23 times faster than RDMA, no matter how we put it. So this RDMA shouldn't replace locality. That's still a golden standard and what we want to optimize for. Now, let's actually start with the paper. What are we talking about? FaRM, Fast Remote Memory, by Alexander Dragojevic and in Microsoft Research. And this is the part of my assignment for the course CS 854 for UWorld. So how do the authors put it? So what is FaRM? FaRM is a main memory distributed computing platform for modern data center hardware. So in short, it's a library to program with RDMA and build stuff with. And the modern data center hardware part just means it's for the future. We think that in the future, everyone uses RDMA. And the main memory part just means, the memory access happens directly in the main memory. Like we don't use storage, we use main memory. What are the use cases? Any high performance, low latency application. This can be anything. They themselves built a distributed database with like a graph store, key value store. Sorry. And they had 167 million key value lookups per second, which is really good, and an average of 31 microseconds of latency. It was very similar to Facebook's Tau, but with significantly better performance, just to demonstrate one possible use case, to have distributed data structures. So what does the FaRM API look like if it's a library that should help you build stuff? So on the one hand, you have transactions that we'll get to in a moment. Basically, allocating free, reading, writing memory, and also committing the entire transaction. You can, have a transaction can consist of multiple operations. Then you have the lock-free transactions, which are like special transactions. And then you have RDMA-based messaging, because this is essentially a message passing interface. So 3 parts. You have shared memory abstractions, you have memory synchronization, and you have communication. These are, the core essence of RDMA. Let's take a closer look at the shared memory abstractions. So you have a shared address space, also called a partitioned global address space, PGAS, which means the entire cluster's memory is shared. Now, it's in the presentation, Alexander made it really clear that it wasn't their intention to make it for convenience, but it was a necessity for efficient RDMA. Why? Well, because if you have like multiple machines that have like the same shared memory, then it has the advantage of, so when you want to access memory with RDMA for read-write operations, you need to have the transfer's starting address plus size. And this is like a lot easier when you have like one consistent virtual shared memory address space. This is the main reason. You don't have to do a lot of arithmetic, which gives you a huge performance boost. And like the management of the memory shared address space is pretty fine granular. You have 2 GB regions, which are identified by 32 bits addresses with 32-bit offsets relative to the starting point of the region. And because the regions are managed with distributed hash tables, the regions are actually virtual rings, and the clusters are managed with Zookeeper. And I talked about the granularity of the memory allocations. It can go from somewhere to 64 bytes to 1 megabyte, and you have like slab allocators for threads. You have blocks for individual machines. You have entire regions for whole clusters. And we'll get to the optimizations at a later point in this presentation. Then, you have the distributed transactions that I talked about earlier, which are just atomic executions of multiple operations for over the shared address space. The operations are just read, write, allocate, free. And you have like a bunch of qualities that distributed transactions have here. Yeah, I mean, I just don't want to throw around buzzwords, so maybe I should explain some of them. So I assume that you know ACID, atomicity, consistency, isolation, and durability. That's like pretty basic. There's like fault tolerance. It's similar to RAM Cloud. I think this paper is kind of built upon RAM Cloud, and it's just logging and recovery in main memory in non-volatile RAM or SSDs. And it allows transparency over like location, concurrency, and failures. Then you have strict serializability. What this means is that the system makes sure that all actions look like they happened sequentially, like one after the other. Then you have optimistic concurrency control, which means that writes are buffered. This is actually almost the same thing as the two-phase commit protocol with RDMA-based messaging, which means that you have like 2 phases. In the first phase, you make sure that you really want to commit this operation, you validate it, and then you commit it, which means that all the writes are buffered and only written at commit time before that the conflicts must have been fixed. And these distributed transactions are like the general primitive, the building block of FaRM. Let's take a closer look at writes, what I talked about right now. Again, you see that you buffer all the writes, then after execution, you lock, you validate, and then you update and lock. Something very special about FaRM that I've talked about previously are the lock-free reads. And lock-free reads are just the atomic execution of a single read, which can be performed with a single RDMA request. And these are strictly serializable with transactions and support co-allocating objects. They're consistent, even if you have like a bunch of concurrent writes happening all around the place. Now, traditionally, on a single machine, these lock-free reads have been implemented by, the state of the art was having a version, which is a 64-bit counter in the header of a memory block to detect inconsistencies. You just locked the counter, updated the data, then you came back to the counter, unlocked it, and incremented it. And when you wanted to read the content, you just read the counter, read the data, went back to the counter to make sure that it hasn't been updated in the meantime, and check that the next number that you read matches with the first one that you read. This is fantastic and all, but in the RDMA realm, this would translate to 3 operations, which is too expensive. We don't want that. So in FaRM, the lock-free reads, first of all, we cache multiple lines. You have multiple cache lines, and we have like a distributed memory, and we don't use 64 bits as previously mentioned, but 16 bits for space efficiency, because we only need to be consistent during the read, and we just track time. And for writes, we just do the same thing we did previously, but for multiple cache lines at once, which are local, we can do that. And for reads, it gets a little bit more complicated. We estimate, or we calculate actually, what the delta of the time for the, what the minimum time of writing this data object would have been, 40 nanoseconds in this case, as an example. And then we set like a threshold for the reading, like the maximum time for reading, which is the minimum time for writing, then 2 times 16, and then we have like a delay tolerance in case the clocks in the machine aren't synced up, and this gets us to 2 milliseconds. And this way, when we're reading with one RDMA request, like multiple cache lines, we just make sure that all the versions match, and it doesn't too long for us to execute this operation. Now, finally, let me just check the time. Yeah, it should be fine. Should be fine. I hope that I'm still like sub 20 minutes, but yeah, I just want to talk about 3 core optimizations that I thought are really interesting in this paper. We'll go through them quickly, okay? So the first one is locality awareness, as mentioned. Being able to do all your operations locally, having spatial locality, having locality-aware optimizations, as they're called, is possible through function shipping. So you just send the instructions to the machine that hosts the data, so you can access the data faster while doing the computation. That's a really smart optimization. Then you have custom NIC drivers, which is actually this improvement or this optimization was necessary because we needed like larger registered memory. So as we had larger registered memory for remote access for the RDMA, we had worse performance. And this happened because the NIC was running out of space to cache all the page tables, because as mentioned, the NICs were responsible for the paging, for the virtual pages. And the largest pages in Windows and Linux were too small. So then the goal was having larger pages and fewer entries in the NICs page tables. And this solution was building FICO, which is a kernel driver that allocates a large number of physically contiguous and naturally aligned 2 GB memory regions at boot time, because 2 GB is the maximum page size supported by our NICs. And this allowed to modify the NIC drivers to use 2 GB pages, and it resolved the problem. And it helped to reduce the number of page table entries per region from like more than 500,000 to just 1. Amazing. And finally, we've got connection multiplexing, which just means that the number of necessary queue pairs, like buffers per thread, or queue pairs per machine would be like 2, then times the number of machines, let's call that M, then times T to the power of 2, because we need 2 queues per thread on each machine. And then by using just a single queue pair per machine, we could reduce that to just 2 times M times T. And if we share queues, we can divide all of that by Q. And this is great because it trades off parallelism for the allocated like memory regions for queue pairs on the NIC. And what the authors have found out is that this was really helpful, but it's like a trade-off between performance and parallelism and memory allocation, and the number of queue pairs. And they suggested that this problem will be solved in the future by using dynamically connected transport, which sets up the connections on demand. And that's about it. I hope this was, oops. Before that, I just realized we also have like the graphs that show that by using FICO, they could still allocate memory regions without the performance degrading. And on the right side, we see that you have to have that intricate balance for Q, which is the number of threads that are shared to trade off memory versus parallelization. But either way, let me know if you have any questions. I hope that this was a good refresher on the paper that we read together. Thank you for listening.